Kia ora team, welcome to this tutorial on energy calculations for level 2 chemistry, structure and bonding. Okay, I know that such questions can be a little bit tricky, but if you follow this method for these types of questions, you're actually going to be okay. So I want to start off by looking at this example question over here. And basically what we're asked to do is we are going to use the following information in this reaction, okay? And we're going to calculate the amount of energy released or absorbed when 120 grams of NO is produced, okay? So here's some important information. We've got this reaction. According to this reaction, in order to produce NO, we are releasing 183 kilojoules per mole of energy. Okay, this is how much energy is being released from this reaction. We want to find out how much energy would be released in a scenario where 120 grams of NO is produced. So first of all, to know how much energy 120 grams would produce, or absorb even, we need to first find out how much is actually in this reaction to produce this much. So this is why I make this sort of a table. So in this top row, it's all the information from the reaction itself, okay? In the second row, this is to do with the context of the question, what we want to kind of figure out, okay? So in this top row, okay, we've got the grams and we've got the energy produced. So it's kind of a bit of ratios that we're dealing with. We're dealing with ratios. And so if we want to find the grams in the reaction, okay, it doesn't give that to us directly. What we're going to have to do is we're going to have to go on a little bit of a tangent and use this equation over here. All right. This equation is basically the moles equation. Okay. So N stands for the number of moles. Little m, stands for mass in grams, which is what we want to kind of try to find out. And then we've got big M, which is the molar mass. So what we know already, if you're someone who already knows what a mole is, you could skip this part of the video. But for those of you who need a bit of a contextual recap, I suppose, a mole is basically a way of simplifying counting lots and lots and lots of things, okay? If we look at a speck of dust, there are going to be so many little atoms packed in that little dust particle. And instead of saying a mouthful of a huge number, we can count it in moles. For instance, it's easier to say a dozen instead of 12 eggs. It's easier to say a triplet instead of 3 people. Okay, so it's a grouping name. So similarly, going with the analogy of 12 eggs is a dozen. This many atoms or things is 1 mole. In 1 mole, you are basically including this many things inside of 1 mole. So imagine if you had to say every time this huge number or more to simply count something. That's way too much. So instead we say 1 mole is this much. 2 moles would be double of this much. So as you can see here, we've got 1 mole of water weighs 18 grams. 1 mole of iron weighs 55.9 grams. And we've got different masses for a mole of everything over here. Okay, and so a mole of say, if we've got a mole of eggs, okay, which is this many eggs, okay, versus a mole of bowling balls, even though they're both 1 mole, the mole of bowling balls will probably weigh a lot more than the mole of a mole of eggs, Okay, so a mole is a grouping word, or basically something that pops a huge number into its own category. So hopefully that makes sense. So anyways, we need to use this equation, this moles equation, to rearrange it to find mass. So what are we going to have to do in this situation here? So we're going to find, using our moles equation, we're going to rearrange it to find the grams of NO, because that is the focus of this question, the grams of NO in this reaction. Okay, so according to the equation, we can see that this many grams, which we're going to figure out, is producing this much of energy. It's contributing to the production of this much of energy. So I can fill that box out. Okay. What are some other boxes I can fill out? Well, it says that we want to know how much energy is released or absorbed when 120 grams of NO is produced. So in context, we're dealing with 120 grams. We need to figure out how much energy that's producing. So first things first, let's figure out the grams in the reaction. Let's complete this top row before we can work out the second row. So the grams of NO in the reaction, I'm going to use this equation. We can see that there are 2 moles. So whenever you want to find out how many moles are within a reaction, you look at the big number in front of this chemical over here. And so if it had no number, for instance, if we look at oxygen, we can see that there's no number. In that case, I want you to imagine that there's an imaginary one. Whenever there's no number in math, okay, you just know that it's an imaginary one. So in this instance, NO has a big number 2, so we know that there are 2 moles of NO in the reaction, okay? We're dealing with only what's in the reaction. 2 moles, and so we want to know what mass is. Do we know the molar mass, how heavy 1 mole of this thing is? Yes, that information is provided. We could see that here. Big M is 30 grams per mole, okay? So that's how much 1 mole would weigh. Okay, 1 mole of NO weighs this much. So we could plug that information in here. Don't get your little m and big M mixed up, okay? It's important to know what's what. So now all we have to do is we need to rearrange, do a bit of algebra to rearrange for this little m value, which is the grams of NO. And so the way I do that is I need to get rid of divide by 30. And so if I divide, the opposite of divide by 30 is times 30, okay? So if I times this whole bottom section by itself, it cancels it out. And if I do it to one side of the equal sign, that means I have to do it to the other side of the equal sign. So this is kind of what it looks like, okay? So I've timesed it by 30 on this side, cancelled it out, and times by 30 on this side of the equal sign to cancel that out. So all in all, what you should get is the mass value equals 2 times 30, which is this line over here, and plug that into your calculator, you should get 60 grams. So we know now, I'm still using the same table, 60 grams in the reaction, okay, 60 grams in the reaction is going to give off 183 kilojoules per mole, okay? So if 60 grams gives off this much energy, how much energy would 20 grams release? Okay, so it's all to do with ratios. And if you're someone who's not gonna pick this up straight away, that's all good. Let me go on a little side tangent to show you and prove to you what ratios, how ratios work basically. Okay, so if you already know this, you could skip ahead to how I solve the rest of that problem. But if you don't know what I'm on about in terms of ratios, just watch this. So if I've got, let's just say I've got 1 pig, okay? 1 pig, for every 1 pig, you are going to, you're a farmer, okay? You're a pig farmer. And for every 1 pig that you have, you notice that they eat 3 apples. okay? For every 1 pig that you have, you notice that they eat 3 apples. So if that's the case over there, you want to figure out, okay, if one pig eats 3 apples, how many apples would 3 pigs eat? Okay, so this is a ratio. If 1 pig eats 3 apples, it's a 1-to-3 ratio. How many apples would 3 pigs eat? So to figure this out, you could do a bit of multiplication, okay? So to get from 1 pig to 3 pigs, you would essentially have to times 1 by 3, okay? So what you do to one side of the ratio, you have to do to the other. So if I've times this top number, or number 1 by 3, if I've times this side by 3, that means I have to times this value over here by 3 to get to this mystery value of how many apples. So 3 times 3 would be 9, okay? That's meant to be a 9. Let me draw that clearer. Okay, so that's essentially how it works, and it makes sense. Let me draw it out. So for 1 pig, you've got 3 apples. For another pig, you've got 3 apples. For the next pig, you've got 3 apples. Count all the apples, you get 9 apples. Okay, so this is how ratios work, essentially. You just need to find that common multiplier that gets you to the mystery box of the ratios. Okay. So back to this example, again, we're kind of still dealing with the same situation, but we're dealing with chemicals instead, okay? So we've got 60 grams. 60 grams makes this much energy. How much would this many grams make? Okay, so what you're going to do is you're going to find out how do you get from 60 to 120. If you use your calculator, you can find out that 60 times 2 is 120. Some of you don't need a calculator for that. But if you're someone who needs a calculator for more complex numbers, of course, I think it's always a wise idea to do that. What you do is you basically take the bigger number, divide it by the smaller number, and then you'll get left with the common multiple, okay? And so in this case, you know that if you times 60 by that number that you just got in your calculator, which is 2, you'll get to 120. So we're just going to do what we did previously. 60 times 2 is 120. That means we have to do the same thing to the other side. So I'm going to times 183 by 2 to get my answer over here of 366. Okay, so this is how it's sort of worked out. And in the end, you could cancel out those units and you'll be left with 366 joules of energy is released, okay, into the surroundings. So to answer that question, okay, we've got 60 grams in the reaction that we worked at using our moles equation. Okay, 60 grams in the equation releases this much. If we were to use 120 grams, it would essentially be 366 kilojoules of energy released. And that's basically the answer for that. Okay, so that is question number 1. That is what you do. If you want to take note of this method, I would take note of this. Okay, this is what you should use for your exams, along with this equation here. Always use this equation to figure out the moles of something. All right, so moving on to another example. Okay, what we have here is question 3b. When magnesium is burned, it produces a white powder according to the equation below. This is the equation. Calculate the mass of oxygen required to produce 1,804.5 kilojoules of energy. Okay, so what is the question actually asking us? I've drawn the boxes, okay, that I need. So the question is asking us, calculate the mass of oxygen required to produce this much of energy. So I'm in the reaction, let's see what we have. Well, we've got the grams in the reaction of O2. This is what we're focusing on, oxygen in the reaction. And we're going to figure that out using our moles equation, don't worry. So I've made that this bit of a star. And the energy that this oxygen in the reaction is producing is this much over here, okay? So it's actually releasing, because of the negative sign, we know that it's exothermic. It's releasing this much of energy, 1,203, okay? So the question is asking us how much grams would release this much energy. So this is kind of different to the previous question, because in this case we're trying to figure out the amount that would release this much energy in the context of this question. Okay, so always start off by filling in the boxes with the information given. All right, so what do we do now? Well, we are going to figure out, first of all, the amount of grams actually within the reaction that is producing this. That's a great starting point always, okay? So I'm going to go ahead, use my moles equation. Okay, I've already flashed you the answer, but I'll show you how I get there. I've got this equation. How many moles are in the reaction? There is only 1 mole of O2, because there's no number beside it, no big number anyway. And so I know that there's 1 mole of oxygen. I'm trying to figure out the little m, the mass, but the molar mass is provided, which is how heavy that 1 mole is, and it's 16.0 grams per mole. So I can plug that into this equation. The way I'm going to rearrange it is I've got 1 mole equals mass over 32.0. The way I get rid of divide by 32.0 is to times by 32.0. That cancels it out. What I do to one side of the equal sign, I have to do to the other. So I'm left with mass equals 32.0 times 1, which is essentially 32.0 grams. Okay, so I can plug that in to this value here. This value is essentially how many grams of O2 is needed or is being used in the reaction to release this much energy in the reaction, okay? So now I can go ahead and fill out that top box. 32 grams of O2 is contributing to this much energy. Okay, so all I need to figure out, okay, is how much of the O2 I need to produce this much energy in context of the question over here. Okay, so a little bit of ratio work. How do I do this? Well, I need to find how can I first get from the energy value in the reaction to the energy value in the context. Okay, so what I'll do is I'll divide one by the other and find out that if I divide this value, 1,804.5 divided by 1,203, I will get this number here. And I'll double check in my calculator that if I times 1,203 by 1.5, I'm going to get this. It's always good to double check that, okay? And so once you do that, that will give you the number that you need to multiply this grams value by. So what you do to one side of the ratio is what you do to the other side, okay? It's like a little bit of a mirror. So times 32.0 times 1.5 will give me, it will give me 48 grams, okay? So by doing this method, I know that if 32 grams releases this much of energy, I will need 48 grams of O2 to create this much energy or release that much of energy, okay? So this is the answer. 48 grams is necessary in order to produce that much energy, okay? So that is the second type of question that you might get. I recommend that you rewatch this video, try do this yourself so you can understand what to do, and tackle all those past exam questions that I've printed out for you and linked in the Google Drive. If there are any questions, sometimes it helps to go through this in person, let me know and I'll be there to help you. All right, all the best for your exams. Hope it goes well. And if you're just watching this for fun, hope you enjoyed this video.